So a common ion present in the solution can have a significant effect on the solubility of a compound. In general, the solubility of an ionic compound will be lower if the solution contains a common ion rather than just pure water. And the reason for this is because the presence of that common ion causes the equilibrium to shift. So if we're looking at calcium fluoride dissolving, produces calcium ions and 2 fluoride ions. If the solution already contains 0.1 molar fluoride ion, then that will cause this equilibrium to shift and less of the calcium fluoride will dissolve. The equilibrium constant is the same, but the molar solubility will be different. So let's calculate the molar solubility of calcium fluoride in a solution containing 0.25 molar calcium nitrate. So we'll start by writing the equation for calcium fluoride dissolving. So we're going to get calcium ion and 2 fluoride ions. And we've got our KSP there. But is the initial concentration of calcium 0 when it's in a solution already containing 0.25 molar calcium? So the initial concentration of calcium is 0.25 molar. The initial concentration of fluoride is 0. And so the change will be that we'll gain, and we've been using S. S is the solubility. How many moles of this solid are going to dissolve? We're going to gain S for that, and we're going to gain 2S for the fluoride because we get twice as many moles of fluoride. So at equilibrium, we've got 0.250 plus S, and we've got 2S. KSP equals calcium times fluoride squared. So that's 0.250 plus S times the quantity 2S squared, and that's going to be equal to our solubility constant there, 1.46 times 10 to the minus 10. Well, do you think X or S is going to be small in this situation? Our equilibrium constant here is pretty small, right? And 0.25 is actually relatively large in terms of a concentration. It's not like, 1 times 10 to the minus 7 or something like that. So let's try S is small. So then we're going to just have 0.25 times 2S, the quantity squared. So that's going to be 4 times 0.25 times S squared. So S is going to equal the square root of 1.46 times 10 to the minus 10 over 4 times 0.25, I believe, is 1. Yes, it is. So the square root of 1.46 times 10 to the minus 10, which is 1.2 times 10 to the minus 5. And if we compare this to the 0.25, yeah, it's 0.005%, definitely small. So this is the molar solubility for calcium fluoride in a solution containing 0.25 molar calcium nitrate. the presence of the calcium here causes the equilibrium to shift to the left, and so we don't get as much dissolving as if there was no calcium present. The molar solubility here is not telling us what the concentration of calcium ion is in the solution. It's telling us how many moles of calcium fluoride will dissolve. Any questions? (2.34 times 10 to the minus 9. Okay, that's different. Okay, so the good news is that it was a typo on the slide and we actually did the problem correctly. So here's a conceptual connection question, common ion effect, in which solution is barium sulfate most soluble? I heard a chorus of C, and I believe that you're correct. Why is it C?
There are no nitrate or sodium ions in barium sulfate.
Yeah, because the solution C contains no common ions with the thing that's dissolving. And the answer is C. Okay, that was painful. Effect of pH and solubility. So the pH can affect the solubility because the pH indicates concentrations of hydroxide and hydronium ions, right? So if we look at the solubility of magnesium hydroxide, at high pH, that has a high hydroxide ion concentration, that means we have a common ion effect from the hydroxide, and that will cause the equilibrium to shift to the left. At a low pH, we have an effect that's not just the lack of a common ion, but this ion, the hydronium ion, will actually react with the hydroxide and chew up the hydroxide ion as it's created while this magnesium hydroxide is being created. And so the equilibrium the equilibrium will shift to the right compared to pure water. So in general, the solubility of an ionic compound that has a strongly basic or weakly basic anion will increase with increasing acidity, decreasing pH. So if you have a basic anion in your ionic compound, making the solution acidic will cause it to be more soluble. Common basic anions are hydroxide, sulfide, and carbonate. Rainwater is naturally acidic due to dissolved carbon dioxide. It's not a super low pH, but it is below 7. And so rainwater will dissolve limestone as it flows through the ground. And the result of this is underground caves. And we get stalactites and stalagmites growing as the dripping water that's saturated with calcium carbonate falls. As the water evaporates, it leaves behind the calcium carbonate. Which compound, iron carbonate or lead-3 bromide, is more soluble in acid than in base? Well, we need to look at what are the ions that are present. So the first one, we've got iron 3 and carbonate ion. In the second compound, we have lead 3 and bromide ion. Are either of these anions basic? Well, let's think about what would the conjugate acid of carbonate ion be? Be hydrogen carbonate.
Wouldn't this be HCO3?
And the conjugate acid of bromide is HBr, which is a strong acid. So this is pH neutral. And this is a weak base. So when iron carbonate, sorry, it's not iron 3, it's iron 2. Iron 2 carbonate dissolves in water. It makes iron ions and carbonate ions. If we have an acidic solution, if we have hydrogen ions, a bunch of them present, can the hydrogen ions react with the carbonate ions? Yeah. There's an equilibrium for those with the hydrogen carbonate ion. So the presence of acid reduces the concentration of carbonate ion in the solution, and that will cause this equilibrium to shift to the right. The iron carbonate will be more soluble in an acidic solution than in a basic solution. That will not happen with lead and bromide, because bromide is the base of a strong acid. It will not associate with the hydrogen. It's just going to sit there. Any questions?